Your mic is muted. So your mic is on mute. Good morning, sir.
Hello.
Yes, sir. Good morning, sir. So we're not able to hear you. So I think your mic is on mute. Yes, sir.
Hello.
Yes, sir. We are able to hear you. Morning, sir. So I think mic is under mute, sir.
Hello.
Yes, sir.
Hello.
Yes, sir. We are able to hear you.
So is the voice okay now? Because I'm not using my this headphone. Without headphone, I'm speaking. Is that fine now?
Yes, sir. We can hear you. We can hear you.
Okay, fine. So I think let us go like this. Yeah. Please go ahead. I mean.
So welcome, sir. Today we have structured
Okay.
For 1.5 hours each session, and for section to the participants.
Okay.
Dr. Surya Prakash sir is current. So can you mute your mic for 2 minutes, sir, please? Because it's echoing over here. So.
Yeah, I already muted.
Thank you, sir. Thank you. Thank you very much. To introduce our speakers for today is Dr. Surya Prakash. Is currently working as an associate professor in the discipline of computer science and engineering at Indian Institute of Technology, Indore, India. He has received his PhD, MS, and BTech degree, all in computer science and engineering from Indian Institute of Technology, Kanpur, India, Indian Institute of Technology, Madras, India, University Institute of Engineering and Technology, Kanpur, India, respectively. His research interests includes image processing, computer vision, pattern recognition, machine learning, deep learning, and biometric security. He has published several articles in referee journals and conferences. He has also co-authored 2 books titled Ear Biometric Localization and Recognition, published by Springer, and IT Infrastructure and Its Management, published by Tata McGraw-Hill. He is a Vishweshwara Young Faculty Research Fellow and recipient of the fellowship grants from the Ministry of Electronics and Information Technology, Government of India under Vishweshwaraya PhD scheme for electronics and IT. He has successfully executed a project titled Development of an Efficient Ear Biometric System and Investigation of Age Invariant Nature of Human Ear, sponsored by Department of Science and Technology, Government of India, during 2015 and 2018 as a principal investigator in the area of biometric security. He is serving as a reviewer of several international journals and has been a member of advisory boards of organizing committees and technical program committees of several international and national conferences and workshops. He has also organized several special sessions in international conference and short-term courses in the domain of computer vision, machine learning, and biometric security. We all welcome you for this FDP, sir. Over to you, sir. Thank you.
Thank you, Professor Rupa, for your very detailed introduction. I think I already am delayed, so let us start directly. I hope I am audible properly.
Yes, sir. Yes, sir. Clearly, sir.
Okay. So in this today's talk, I'm going to talk about one of the important topics of biometric research of current time, which is biometric template security. So as the name suggests, I mean, there are three words in the name, in the title: biometric, template, and security. So one by one, we will go through them and then try to understand what is biometric. I hope this might be very well clear to most of the participants. But then we'll see what we mean by biometric template, and then we'll understand what exactly we mean when we say biometric template security. Okay. So some of the slides might be redundant because I mean they're very basic slides. So yeah, if you are aware of I mean the biometric area. All the participants, can you please mute your mic? I mean, if you are not speaking. Okay. Let us start with the introduction to biometrics. So biometrics basically refers to metrics related to human being or some unique characteristics which are associated with the human being and which are unique, I mean, in some sense. And if these characteristics are unique, then we can use them actually to recognize people. So basically in the biometrics, we deal with such human characteristics which are unique with respect to people. And then since they are unique, we try to use them for recognizing people. Some of the examples that we we see for these traits, they include face, fingerprint, iris, hand geometry, ear, palm print, and so on. If you just look at the details of these traits, so some of them are actually physically associated with our body, and some of them are associated with us in our behavior. So based on this, we can actually classify these techniques in two categories. One is the physiological biometric category, where you see the examples like fingerprint, face, palm print, and so on. All the biometric characteristics or the biometric traits which are associated with our body, and the other characteristics which are related to our behavior, they come under the behavioral biometrics. So the common examples here are like signature, gait, typing pattern or typing rhythm when we type on keyboard, our voice, and so on. Okay, so these are the popular examples of physiological and behavioral biometrics. Now, what we expect in an ideal biometric trait. So, for example, we have many biometric traits such as face, fingerprint, ear, iris, so many things. So when we are going to select a particular trait as biometric, what are the expectations? So the very first expectation from the characteristic of the human characteristic that we are going to use as biometric is that it should be unique. Because if it is not unique, then I mean we can't be able to distinguish people from one to another. So whatever biometric characteristic we are choosing, let's say face, so obviously it should be unique. So like for example, we choose face because face is unique to everybody, iris is unique to every individual, and so on. And second thing, so uniqueness is I think the most important thing. Another is the permanence. How permanent is that biometric with us? So you might be thinking that every biometric is permanent, but there are some biometrics, for example, fingerprint. When we use our hand or our fingers, they deteriorate over time. So, for example, for the laborers, you might find fingerprint very weak. Okay, so another is that the biometric should be permanent. And the third requirement is the measurability. So we should be able to measure that particular biometric. So we may have something very unique with our body, but if we are not able to measure it, then we will not be able to use it for the biometric recognition purpose. So third requirement of any biometric trait is that it should be easily measurable. Okay. Performance is another criteria where, I mean, so since we are going to use biometric traits for recognizing people, so any trait which is good in recognition will be like preferred over the others. So performance is another criteria based on which we select the biometric traits. Another important criteria is acceptability. So you may have some very good biometric, but if the people are, let's say, not accepting it to use, then it doesn't have any of any use. And the last point that I just wanted to mention is the circumvention, which basically means that how easy it is to spoof that biometric. Okay. So with respect to all the biometrics that we know, we can just think about all these characteristics. For example, let us just discuss few of them. So for example, permanence, I told that fingerprint is not very permanent, but let's say face. So face is obviously very, very permanent with the body. Like that, I mean, you can say that if permanence is considered, face is much better than any other biometric. Similarly, let's say acceptability. If you talk about acceptability, so you might have observed many people are not willing to give our iris. Like whenever this Aadhaar recognition happens, people are like skeptical. They are like thinking that light that goes into their eyes, that may create problems, right? So that in terms of performance, if you see, the iris is considered very high performing biometric trait, but in terms of acceptability, you may find that it is not as acceptable as other biometric traits. Okay. Fine. So let us move ahead. So again, this is again a very basic slide. So why do we need biometrics? So obviously, as we just discussed, biometric is used to recognize people. But what is the problem with other traditional things that we have been using for recognizing people? For example, ID and password. These have been used for recognition of the people. PIN has been used for a long time. But what are the problems with these kind of things? The problem is that suppose if we are talking about PIN or password, somebody can guess it. Or if you're talking about, let's say, the ID, somebody can forget carrying the ID, and so on. So these are some issues if we talk about the traditional biometric systems. But in case of in case of traditional recognition systems, now in case of biometric systems, many of them are actually overcome. For example, if you are using a biometric for recognizing people, we don't need to do anything specific to carry it. Right? So always, we don't need to remember it. We have to, whenever we travel, we always carry our biometric. Similarly, it is relatively difficult to imitate, though now biometric traits like fingerprints and all, there are cases where they have been spoofed. But it is relatively, if you compare with the password, imitating fingerprint is, for example, difficult, and physical presence is not required. Physical presence is required in this case. In case of password, somebody can just use your password or PIN to, let's say, access your ATM or your account. But in this case, if you are using a fingerprint, your physical presence is required. Okay. Yeah. These are the basic steps when we use any biometric system. The first is the enrollment step, and second is the authentication step. Whenever we have to use any biometric system, we have to first enroll ourselves with the system, and once we are enrolled, then we can use it for the authentication. For example, let's say the example of ATM. So if you want to use ATM with the help of your fingerprint, then first you have to go to your bank, and then you have to enroll yourself. And once you are enrolled with the system, then next time when you go, you can use it for the authentication. In detail, these are the steps which we follow when we do biometric recognition. So the very first step is that we have to collect the data from the biometrics that we are using. So let's say we have decided to use face biometric for certain applications. So we need some sensor to collect the data from the biometric, and then we need to do pre-processing. So for example, for the face, the sensor could be a normal CCD camera. And then once the data is collected through CCD camera, then we need to do some pre-processing to improve the data. Like, for example, the data may be noisy, or it may have, let's say, if you're talking about face, so it maybe have some pose issues or illumination issues. So all those issues are tried to handle at the level of pre-processing. So once we do the pre-processing on the data, we expect that the data is clean and suitable for further processing. So we extract the features, some unique feature from the data here, and then collectively when we put all these the extracted features together, it makes a biometric template. And if we are enrolling, if you are using the system first time, then you have to go through the enrollment process, and you have to register yourself with the database. And if it is the second time, or if you're using the system after enrollment, then whatever features you have provided, they will be compared with the features available in the database, and based on the matching results, we will say whether the person is accepted or not accepted. Now, in this whole flow chart, this is the important thing, because we are going to discuss about the security of this template. In terms of the features, these are the two examples given here. In case of fingerprint, I think most of you must be aware of this. From the fingerprint, in the fingerprint, there are a few unique points which are called the minutia points. And as feature, in most of the algorithm, these feature points are used. So, and these points are actually, if you closely see these fingerprints, you find that there are some flowing ridges in the fingerprint, and these ridges at some places they abruptly end, or they bifurcate. So those points where they bifurcate or they abruptly end, they are called the minutia point. In the subsequent slide, I'll show you the detailed picture of that. So as a feature from the fingerprint, normally we extract these unique points, and that makes the template. Similarly, for the face, maybe in a very simple case, we can assume that let's say we are doing face recognition with the help of some measurements that we do from the face. So let's say we are considering the width of the eyes, and then let's say the location of the nose tip, or the distance of the nose tip from the endpoints of the mouth and all that. So once we, let's say, extract these features or these points, we can extract some features from them that we can use directly these points as feature, or we can compute some values from these features, and then we can use them for recognition. Okay, so for example, when we are moving from feature extraction to template generation, if you're directly using the feature, then whatever we have in the feature here and here, it will be, same. But let's say whatever features we have extracted, you are going to again compute some information from that. So then you will find that what you have here and what you have here will be a little different. Right? For example, in this case, your features are these points, but maybe you can extract some distances from them, and that makes your template. Okay. So out of all these steps that I discussed, pre-processing, feature extraction, template generation, and matching, we are going to focus more on this particular part, because we are going to talk about the security of the biometric template. Okay. In a typical biometric system, let us just first understand how we what are the features, and then how we do the matching. So as I just said, that in a fingerprint image, you have flowing ridges. As you see, these green lines that they are flowing, these are called ridges in a fingerprint. And these ridges are ending at a particular place. Sometimes, like for example, if you see this flowing ridge here, it is ending at this point. And similarly, if you just see this point, the flowing ridge, let us consider this ridge. So when it comes here, this bifurcates in two parts, or two ridges. So these points where these ridges are ending or they are bifurcating, they are called the minutia points. So whenever in a typical biometric system, when we match these two given fingerprints, we try to find out how many points in the two fingerprints are matching. So matching in the sense, for example, if you have a point at, let's say, a particular location here, we try to see at that particular location or in a little neighborhood if the same point exists or not. So like that, we from one fingerprint we see all the minutia points and try to find out the respective minutia point in the another fingerprint, and then based on how many matchings have been found, we declare the matching results or the matching score. Okay. Now what are the issues? Till now we have talked about good thing about the biometric, but what are the issues with the biometrics? So let us first discuss these issues, or maybe one of the issue that we are going to discuss here, and then we'll go into the details of that particular problem. One of the major issues with the biometric system is that these systems can be attacked, and whatever biometrics we have stored in the database, that can be stolen. And if suppose that biometric is stolen, somebody can actually create a spoof or parody of that from that stolen data, and then can pose as someone who the person does not actually represent. Okay, so one problem is that these databases can be attacked, and if the databases are attacked and somebody is able to get hold of your biometric, then a spoof or a parody can be created from that biometric, and that can be illegally used. What is the problem here? So these problems are in other things also, like for example, password. Somebody can steal your password, or somebody can guess your PIN. But the good thing with, in some sense, you can say, but with those systems is that if you lose your password or if you lose your PIN, you have option of just going and changing it. But in case of biometric, if it is stolen, then we don't have option of changing our biometric, because biometric is associated with our body. And if our, let's say, fingerprint is stolen, or the fingerprint features are stolen, then we cannot have another fingerprint and then get a new set of features. I mean, maybe, for example, in case of fingerprint, you have 10 fingers, so 10 times you can use it. But the cases like face or other biometric features, you don't have option of any alternate such biometric, right? So that is why we are concerned about securing the biometric data, because once the biometric data is lost, it is lost. It is lost forever. Okay. So this is the main issue with the biometrics that we are going to discuss here. So in case of, I mean, this demonstrates that in case you lose your password, I mean, you have option of changing the password. But if you lose your biometric, or let's say you use your fingerprint of a particular finger, you cannot recreate that finger and then get your biometric again, right? So that is why whatever data we are storing in the biometric in your biometric database, or whatever features or template we are creating from the extracted biometric, we are very much concerned about securing it. Okay, so that is why we are going to talk about securing biometric template in this presentation. Okay, so what basically we want. So in biometric systems also, we want revocability. So revocability basically means that whatever you have stored already in the database, you should be able to replace it with the new data, which actually we are able to do in the case of password. So in case we lose our password, we have option of revoking our old password and changing it with the new one. But such thing does not exist in case of biometrics. For example, if you are using fingerprint, you have extracted your minutia points from the fingerprint, and those, let's say, minutia points you are using as your biometric features, and that is why you have stored these features in the database. Now, let's say someone steals these features. So now, as long as your fingerprint is with you, these features will be again. If you scan your fingerprint, if you again scan your finger and get the fingerprint, you will again you're going to get the same set of features, same locations, and all that. So that is why, I mean, if you lose these features, they are, I mean, in some sense, you are losing your biometric permanently. So that is why we want here that it should be revocable, which basically means if we have, let's say, lost this biometric because in the attack in the database, we should be able to replace it with the new one. Now, one thing is very clear that since as I said that this biometric is permanently associated with with our body, or these features are, I mean, since these features are coming from a particular biometric, and that biometric is permanently associated with our body, we cannot change the biometrics. That means we do not have option of revoking this and then getting new set of features, right? So that is why in case when we talk about fingerprint biometric or any other biometric, we don't directly store the features which we extract from the fingerprint or from any other biometric. What we do some kind of transformation on the features so that what we store is not exactly what we have obtained from the biometric. So in case when this is, let's say, compromised, then we'll change our transformation and we'll get new set of features and then we'll store them. Okay. So this we are going to see in detail. One thing that you can just remember from here is that if you want revocability in our biometric system, the very first requirement is that we should not store our original features. We should do some transformation on the features, and those features should be only stored in the database. Because if you are storing our original feature and if they are lost, then we don't have any option of getting new set of features. Okay. So what we expect from any ideal biometric system? So the very first thing that we expect from an ideal biometric system is that the template that we are storing in the biometric system, that should be revocable. That means in case you find that your template or your biometric is compromised, we should be able to change it. And now all the other associated things that I mentioned here, they are basically related to revocability only. So when we are talking about revocability, the templates that we are generating. So I hope one thing is clear here, that when we are revoking a stored template in the database and generating a new template, ideally we can generate infinite number of templates, right? Whenever a template is compromised, we can just again generate a new template and then use it. So when we are generating these multiple templates, they should be diverse. They should be different from each other. So let's say at one point of time you have stored one fingerprint template and you found that that is compromised, and let's say you are going to store a new template. So that new template should be very diverse from the previous one, because if it is similar to the previous one, then there will be security problem. So the templates that we are generating here, they should be diverse. Third thing is that these templates should be secure. When we are implementing revocability, as I just mentioned, we are basically going to transform our original features, and then whatever we are going to get after that transformation, we are going to use that as our template. So when we are, let's say, doing some transformation to get new set of features, from that transformed feature set, it should be difficult to achieve the original feature. Okay, that we mean by security, because if it is, let's say, you have a fingerprint template and you have applied some transformation and you got, let's say, a new set of fingerprint features, FT prime. So it should be very difficult, or we should say it should be almost impossible to again do some kind of inverse transformation and get these features. Because if this inverse transformation is possible, then again there is no security in this feature set. Because if someone gets hold of this, then by applying that inverse transformation can get an original feature. So that is why whenever we are implementing such system which is revocable, security is the prime concern, and whatever template we are generating, it should be theoretically or even practically it should be impossible to get back the original set of features from the transform template. Another requirement is the performance. So again, as I said, that you are going to generate a transformed set from your original features. So because of this transformation, you should not lose the performance. So we can take the example of fingerprint. Let's say in place of using original feature from your fingerprint, let's say we have transformed them and we got new set of features. But whatever performance we were getting from the original features, we should also get from the new set of features. If this transformation is deteriorating the performance, then also it cannot be considered good. It may provide security, but then it is deteriorating the performance, so it may not be acceptable. So when we are implementing revocability, the new with the help of some transformation, whatever new feature sets we are getting, that should not deteriorate the performance. Okay. So out of all this property that I just mentioned, revocability is the important one, because all the other three are related to revocability. So let us discuss this in more detail. So I just mentioned revocability basically mean that in case when your template which is stored in the database is compromised, we should have option of revoking it and changing it with a new template. Okay, so to achieve this, as I already mentioned, what we are going to do, we are not going to store our original features in the database. We are going to do some kind of transformation on the features, and then those transformed features only we are going to store in the database. Okay, so all the biometric template security techniques which are available in the literature, they can be actually classified in two categories. One are the cancelable biometrics, and another set of biometric template security systems are called biometric crypto system. We are going to talk more about cancelable biometrics here, and I'm going to discuss two techniques here. They also fall under cancelable biometrics. And whatever I mentioned that we are transforming the features and then storing the transformed features, it is more true with the cancelable biometrics. So in case of cancelable biometric, we are going to use transformed set of features, and then we are going to store transformed feature as template in the biometric system. In case of biometric crypto system, here also the idea is the same. We are trying to secure our biometric features, but here the techniques are a bit different. They are not storing the transformed features, but in some other way with the help of keys, the security is actually maintained here. So I'm not going to talk more about this here. Let us discuss the first case. So in case of cancelable biometrics, as I mentioned several times, we are going to do some kind of transformation. So here, let's say you have a original biometric template T, and in this case also we are going to use some set of keys normally to do the transformation. So for a given template T and for a given key K, we do some transformation on the original biometric template, and then we get this transformed template, and we use that transformed template for the we store this transformed template in the database, and then we use it for the recognition. So whenever we are going to enroll a person with the system, we are going to get the transformed template from the person and going to store in the database. And when we are going to recognize person, when let's say a test sample comes, we are again going to perform the same kind of operation, same kind of transformation on the test sample, and then whatever we get on from the test and from the stored sample in the database, we compare them, and then based on that we decide the results. So here we are not matching. When we have to recognize a person, we are not matching their original biometric template. We are performing the matching in the transform domain. So for the original template also, this is the we are getting the transformed template, and for the query template also we are getting the transformed template, and then we are trying to match. We can understand this with the help of this example, this diagram here. So let's say this is the person who is going to use the biometric system. So you have got some features from this person, right? I mean, this could be anything, like maybe face features or fingerprint features, anything. So this set A actually contains the original features that you have extracted from the person, and you have also used a, let's say, key K. With the help of this key K, this original feature sets are transformed. And when you perform this transformation, what you get, as I just said here, you are performing transformation on the original set, so you will get transformed features. So these transformed features only are stored in the database. Now, when next time the person comes and you want to test the system, then you collect the probe data from the person, and then with the help of the same key that we have used at the time of enrollment, we get transformed template. So this BK actually represents the transformed template. And then when you compare this transformed template with the one which is stored in the database, obviously since this feature set or this probe vector has come from the same person or from the genuine person, so you will find that whatever is stored in the database and whatever you have got here after transformation, they will match, and then the match will be successful and you will be able to use the system. But in case of imposter, what will happen? Let's say somebody is trying to pose at someone else. Then in that case, first thing, the feature will be different. Whatever features you are going to get here, they will be different. And similarly, the person will also not have the key that we have used here. So whatever you are going to get from here in the transformed domain, it is not going to match what is already stored in the database. So in that sense, we can say that this person will be rejected. Okay. So in the domain of cancelable biometric, which we are discussing here, there are some common examples. Like we use block scrambling, distortion-based template security, surface folding. We'll see this with the help of few examples. And in all these examples that we are seeing here, in general, we can say that whatever we have in case of cancelable biometric, we are going to implement that with the help of a transformation. And that transformation need to be non-invertible. As I just mentioned a few slides back, that this transformation should be non-invertible, because if it is invertible, then from your transformed features, the original features can be obtained, and that is not actually desired. Okay, so whatever transformation function we are using in all these techniques, we'll see that they will be non-invertible. Okay, these are some examples from these techniques. So in block scrambling, whatever input data we have, we first try to do some kind of transformation on the input data itself, And then after that, only we extract the features. For example, we are trying to, let's say, use a fingerprint in the biometric system. So before using the fingerprint, we have just scrambled all the blocks, and then whatever new set of blocks we get, we extract the features only from those blocks, right? And then when we are coming from here to here, this process is unique. How did we scramble them? That you can say that in some sense it's a secret. So if somebody wants to go from here to here, it may not be feasible. Okay? Sometimes we apply the distortion on the input data based on image morphing. For example, in case of face, in place of using original face, we can morph it. We can change the face by using some transformation, and then whatever new face we get, we extract the features from there. So, in case if let's say your feature that you have obtained from this transformed or morphed face, they are compromised, you can again get a new kind of morphing, and then again you can extract the features. Okay. So here you have option of changing that transformation or changing the key. And once you get the new transformation based on a new key, what you get after transformation will be different, and thus the feature that you are going to get from there, they are also going to be different. Okay, so in all these examples, we see that in both the cases, whatever features we are, whatever transformation we are doing, this transformation we are doing on the original data, for example, on the original face data or on the original fingerprint data. But this transformation can be also applied on the features. For example, you have from the fingerprint, you have extracted some features, and then you are performing some kind of transformation on these features to, get a biometric template. Okay. So this transformation can be performed in the, let's say, your features are represented in Cartesian coordinate system, so that can be performed in Cartesian coordinate system. It can be performed if you have a polar coordinate system. They can be, this transformation can be implemented in polar transform in the polar coordinate system, and so on. Based on these transformations, you see there are multiple techniques which are existing in the literature. I'm just mentioning few of them here. So one of the technique that we are going to discuss here in detail is the fingerprint cell. I hope till this point it is clear that whenever we are going to get a biometric template with the help of any technique that we are going to discuss here, this is going to be a transformed template. This is not the template that finally we are going to get in all these techniques is not going to be the original set of features. The template is going to be defined with the help of new set of features or in some new ways. In case of fingerprint cell, as our basic features, we are going to use the locations of the minutiae point only. But based on these locations or based on these minutiae points, we are going to extract some new kind of representation for the fingerprint, and that new representation only we are going to use as our biometric template. So from this side, let us try to understand what are the features we are going to use in this technique. As I mentioned, we are going to use minutiae points to implement this technique. So given fingerprint image, we are extracting the set of minutiae points or set of points where these ridges are ending or bifurcating, and we are also going to use one more point from the fingerprint that is called the singular point. And in some sense, you can say that the singular point in the fingerprint is the point almost at the middle of the fingerprint. And in terms of technical definition, if you go through all these ridges, you find that there is some curvature in these ridges. So if you keep moving in these edges from this direction to this direction, you will find that the curvature keeps increasing. So the point where this curvature is the highest, that point is actually called the singular point. So in this fingerprint image, you find that this particular point here has the highest curvature. So that is called the singular point. So in this technique or in the technique of fingerprint shell, we are going to use these minutiae points along with the singular point to implement this technique. Okay, and from these minutiae points and with the help of this singular point, we are going to actually extract some distances. These distances are the distances of these minutiae points from the singular point, and whatever these distances we are going to get here, those distances we are only going to use as features to generate the template. So we'll see that for a given fingerprint image like this here, in our traditional system, if we, let's say, want to extract the features from this fingerprint and want to store it in the database, what are the features we will extract from here? We'll extract the setup, let's say, locations X and Y. And sometimes we also use another feature called the orientation of the fingerprint, which basically, I mean, if you put a tangent on your wrist at the place of your minutia point, whatever angle your tangent makes, that is actually called the orientation of that minutia point, and that also sometimes used as feature. So in our traditional system, our features are the template that we could have obtained from this fingerprint would have been a set of X, Y, and theta values. But here we are saying that we are not going to store this these set of features in the database. What we are going to do, we are going to get from these features a new representation, and this new representation is only going to be stored in the database as a representative of the fingerprint that we are using here for in the biometric system. Okay. So now let us see, given these original features that are obtained from the fingerprint, how to construct this new representation. So what are the steps that we are going to follow here to implement the fingerprint shell? First is we have to extract the minutia points. So obviously, because this technique is based on the minutia point, so first we have to extract the minutia point, and also we require the singular point, so we have to extract the singular point from the image. And then we are going to calculate, since as I mentioned, this technique is based on the distances of the minutia points from the singular point, so we are going to calculate the distances of the minutia points from the singular point. Now, once we get this, with the help of this information, we are going to generate the fingerprint shell, which is a kind of curve as we observed in the previous slide. So to generate this curve or to get this new representation, what we have to do first, we are going to first sort the distances that we have obtained, and once the distances are sorted, and also we have to decide one key. We'll see what is the importance of this key, and with the help of the sorted distances and the key that we have decided, we'll see that we will be able to construct the curve that we are going to use as our new representation. So let us see how we are going to construct this curve. So first, given the minutia points and singular point, we are calculating the distances, and let's say those distances are d1, d2, d3, and so on. And once we get these distances, we sort them in ascending order. Okay, so let us assume that in this d1, d2, d3, the sequence is the sequence that you get after sorting the distances. So we can say that d1 is less than d2, d2 is less than d3, and so on here. So once these sorted distances are obtained, we add the value that we have just used as key on these distances. So d0 is added to all the distances that we have obtained. So it becomes d0 plus d1, d0 plus d2, d0 plus d3, and so on. Now, once we get these distances, after adding d0 to them, we make the get that new representation, and this is the procedure for them. Procedure to get that new representation. Let us see this with the help of an example. So what we have obtained till now from the fingerprint, we have extracted the minutia points, singular point. From the singular point, we have computed the distances of these minutia points, and then to those distances we have added d0. So we have d0 plus d1, d0 plus d2, and so on. Those values are there. Now, with the help of those distances, we are going to construct this new representation, which is going to come in the form of a curve like this. So let us understand the procedure of this construction. So on the Cartesian coordinate, we can just assume one point on the plane. It can be any point. Let us, for the simplicity, this is 0, 0, but it can be any point. So we start, let's say, from 0, 0. At 0, 0, we put a horizontal line like this in this direction of distance d0. So in this direction, we travel d0 distance and put this line here. So from this point to this point, we have the distance d0, which is coming from the key that we have considered. So D0 was the key that we considered for this process. Once this line is put here, here we are putting a vertical line, and on that vertical line we are cutting this line of length D1 plus D0. Okay, so as we do that, we get a new point here. So this becomes our new. First point was this one. Second, with the help of this D1 plus D0, we got a new point. Now again here, we are putting a line which is perpendicular to this line. And on this line, we are cutting a segment of distance D2 plus D0, which is the next distance. And since this D2 plus D0 is more than D1 plus D0, you will find that this intersection is possible. If this distance would have been less than D1 plus D0, you will find that when you are putting when you are trying to get a segment, you will not get this point. Okay, but since D2 plus D0 is more than D1 plus D0, it is guaranteed that you will get this point here, which is D2 plus D0 distance from the origin. Okay, and similarly again we put a line perpendicular to this one here, and then on that line we cut a segment of D3 plus D0, and since again the D3 plus D0 is more than D2 plus D0, again you will be able to cut this segment here, and likewise we keep doing. So if you can imagine that when you do it for several points, you will find a curve like this, which will be kind of a spiral curve. Okay, so if you have lots of minutiae points, you will find that this curve will go like a spiral curve. So from in this technique, in the fingerprint shell, we do not use directly minutiae points to make the template of the data biometric that we are using. From this biometric, we are extracting this new representation, which is in the form of a spiral curve, and this is used as a biometric template in the database. Okay. Now, what is the important? How it is helping in securing our biometric data here? So we are going to discuss that in detail after a few slides. But one thing you can understand from here that we are using a key D0 to construct this curve, and everything in this figure you can see that everything is based on this D0. If you just change this D0, then you will find that this curve will be a different curve. Okay. Other distances we cannot change, D1, D2, D3, they cannot be changed because they are coming from the fingerprint. So they are permanently associated with us. But this value of D0 we have decided, and we said that this is going to be a key. So this key can be changed. And if you change this key D0, we'll see that we'll get a new set of features or new kind of curve here. So we can say that here, if let's say this template is compromised, we can just change our D0, and from our original features, we can get again another new template. And when we say that this template is compromised, it means only the features that you have stored here, they are compromised. The original minutiae points from where you have generated this curve, they are not compromised because if this transformation is irreversible, you cannot get the original minutiae points from this representation. So just by using a different key, you can get a new set of features or new kind of curve, and that way you can achieve the revocability. We're going to see this in detail after a few slides. Now, the question comes how to match these two curves. So as I mentioned earlier, that when you have your features represented in terms of minutiae points, we try to find out how many minutiae points are matching with respect to the two fingerprints that we are matching, and based on that count, we tell the match score. But in this case, our representation is not in terms of minutiae points. Our representation is in terms of a spiral curve here, which is a geometric shape. So, most often to compare two given geometric shapes, we make use of house top distance. So that house top distance can be actually used here to match the two templates in the transform domain. So if you are matching two fingerprint images, we can, I mean, obviously we are going to have the spiral curve for both of them. And then since both of them are going to be geometrical structures, you can just make use of Hausdorff distance to match them. Okay. Now let us understand in detail what are the achievements of this technique, or how we are going to achieve revocability or diversity, security, or diversity in this case. So as I just mentioned, how we are going to achieve the revocability in this case? We are going to achieve revocability by changing the value of d naught. As I just explained in the previous slide, that if you change d naught, your entire curve is going to change. So if, let's say, whatever you have stored, I mean, as I already mentioned, if you compromise this curve, you can again use another d naught and then get a new curve. Okay? So that way, whatever template you are going to store in the database, this is totally revocable, because a new template can be very easily obtained with the help of a new d naught. Okay, so that way it is revocable. And whatever transformation that here we are using, that actually irreversible. So from this curve, it is not possible to go back to original set of features. So that is why we can assume that, or we can say that this technique is secure. And to understand the diversity, let us see this example. So diversity basically mean when in this, let's say in this particular case, if you are changing d naught, whatever transform template we get, that should be very different from the another template that we got for a different d naught. Okay, so let us see here. Let's say this is the fingerprint image given to us, and we have two keys, key 1 and key 2. These keys are applied on the same fingerprint. So from these features, we apply key 1. You can say this is, let's say, d naught, and this key 2 is d naught prime. Okay, so when you apply d naught, we get this spiral curve. And when you apply d naught prime, another key, we get this spiral curve. Now we see that though they have been obtained from the same fingerprint, they are looking very different. In this case, this is little compact and it is, let's say, ending here. But in this case, it is little sparse and ending here. So you can very clearly see the difference between this template here and this template here. You can the important point to note here is that they have been obtained from the same fingerprint impression. Okay, so we can say that whatever due to implementing the revocability, whatever new templates we are generating, they are very different from each other. For key 1, what you get is different from what you get for key 2. Now, whatever this new representation we are getting, is it coming same for our different fingerprint impressions that we give at different instance, different time instances? So to see this, let us try to consider another impression of the same person. So let's say this is the first impression of that person, and this one is the second impression. Let's say at the time when the person is coming to use the system. You can assume that this was at the time of enrollment, and this is happening at the time of when the person is going to use the system. So now from this fingerprint image, which is different from the previous one, on this we are going to use again the same key, and let us see what we get here and whether it is same as what we got previously or not. So when we are using key 1 on this fingerprint, we get this template, and when we use the same key on different impression of the fingerprint of the fingerprint of the same person, we get this template. Now, if you observe them, they are looking quite similar to each other. Right? If, for example, in this case, this is ending here, this is also ending here. Other points that we will see here, they are also coming almost at the same location. Okay, so though these two templates have been obtained from the different fingerprint impressions, since the key was same, they are coming very similar. They are very similar. If you, I mean, again, you should compare them. They are looking very similar. Now let us see if you change the key, what happens. So on this impression, let's say you have just to revoke this template, you have used another key. So when you use the another key, new key, let's say key 2, you get this template. Now, if you compare this template from the previous template that you obtained for same key, you see that this is again coming very similar. If you compare this template and this template, again they are very same. But if you compare the templates across the keys, they are looking very different. So for key from this impression also, whatever template you have obtained, this one here and this one here, they are very different because this is for key 1 and this is another for key 2. So they are distinct. So when you change the key, this example shows that when you change the key, the new template that we get, that is different from the template that we obtained for the other old set of keys. So that way, the two things that we can, find out or we can conclude from here. One is that this process is revocable because when you change the key, you get a new kind of representation. Again, for this impression, I am just reiterating. For this impression, when you change key from key 1 to key 2, you get new kind of representations. Similarly, for this this impression here, when you change key from key 1 to key 2, again you get a new set of representation. Second, from this example, we can conclude that the templates that we are getting here, they are diverse because from the same impression, if we from the same impression for different keys, whatever templates we are getting, they are not matching to each other. So that way they are diverse, and we are able to maintain the diversity in the templates. Okay. So this was the first technique, which was the fingerprint shell, and there are some issues that we highlighted in this technique, and then proposed a new technique, which we call fingerprint shell with impringible features. In the previous technique, if you see, this was completely based on this key D0. Though it is difficult to guess the D0, but one thing, if you can see from this picture, that let us say, I'm again repeating, D0, guessing D0 is very, very difficult. But if let's say someone gets this D0, then with the help of this D0, other original values can be, other distances can be very easily obtained. Because once you get the D0, then if you subtract that D0 to D1 plus D0, you will get D1. Subtract this to D2 plus D0, you will get D2, and so on. So if this D0 is known somehow, then all the distances can be obtained. And since these distances are the distance of your miniature point from the singular point, if these distances are compromised, you cannot get new distances because again, if you compute the distances from your fingerprint, they are going to come same because your miniature locations are not going to change. Okay, so everything relies here in this technique on D0, and if the D0 is compromised, then this whole system can be compromised. To just put more security on this and secure the original features, we propose this technique called fingerprint shell with impringible features, where we are using 4 set of keys, 4 keys in the set: P0, Q0, M0, and R0. We'll see that this M0 that we are going to use here is same as D0 that we used in the previous technique. Other keys we'll see that they will be used differently, but this M0 will be used for the same purpose for which we used D0 in the previous case. Okay. So in this technique also we are going to implement a transform with the help of keys, and in place of using one key, we are using a set of keys, and in total we are using 4 keys. So for this system, as an input, we are expecting the fingerprint image from where we will be extracting the miniature points, and then this set of user key. This also need to be supplied at the time of implementation of this technique. So once we get this input with the help of the features that we are going to obtain from the fingerprint, and with the help of these keys, we are going to generate a new curve. In this case also we'll see that this will be a kind of a spiral curve, but this curve will be more secure compared to the previous one, and this will be also a 3-dimensional curve. In the previous case we saw that was only 2-dimensional curve, but this will be a 3-dimensional curve. Okay, so for input, I just said we have the input is the fingerprint image, and this key set that we are going to use. And the steps that we are going to follow to implement this technique are as follows. We are going to first extract the miniature points and the singular point. And then from this miniature point and singular point, we are going to compute the distances of all these miniature points from the singular point. And whatever distances we are going to get, if you remember in the previous technique, we are directly going to use them to construct the spiral curve. But in this technique, we are not going to use those distances directly. We are going to modify them. And then those modified distances are only going to be used for the spiral curve construction. The idea here behind modifying the distance is that even though if your distances are compromised, you don't lose your original distances. You only lose your modified distances. So that is why in place of using the old original distances, we are using the modified distances. And from the modified distances, we get a spiral curve. And that spiral curve actually with the help of, we'll see, ridge count. I'll just tell what we mean by ridge count. With the help of this ridge count and the spiral curve that we obtained here, we get a 3-dimensional spiral curve. So, as I just mentioned, the first requirement in this technique is also the singular point. So we first extract the singular point, and these are the techniques that we are using for extraction of the singular points. You might be seeing there are two techniques here we are mentioning, because if you just go and study this in detail, you'll find that there are multiple types of actually singular point in the fingerprint image. So to extract all those singular points, we are using multiple techniques, right? Okay. Once the singular point is computed, we extract the miniature points, and we are also going, in this technique, we are also going to use the orientation of miniature points. So along with the location of the miniature points, we are also extracting their orientation. And as I just explained a few slides back, this orientation is nothing but the angle that tangent that you put on the wrist at the point of the miniature location, whatever angle that this tangent makes with your horizontal axis, that actually defines the orientation. So for all the miniature points, you put a tangent at the particular wrist and then measure its angle, and that defines the orientation. So we are, from given fingerprint, we are going to extract, in some sense, you can say four values. One is the location of the singular points. Another is the location of these miniature locations, which are the locations of the points where these ridges are bifurcating or they are terminating. And the last thing that we expect from here is their orientation. Okay. Now this is the detailed details about the technique. So the very first thing that we do here, and just let me again go back to the steps that I mentioned here. So what was the first step? It was to extract the miniature points from the fingerprint image, to extract the singular points from the fingerprint image. And then from there, the next step was to get the modified distances. So in that diagram, we are trying to understand how to modify the distances. Once the distances are modified, whatever we get, actually we call those distances as the secured distances or secured modified distances. And once the secured modified distances are obtained, then we go to the next step and then make the 3-dimensional spiral curve. So let us see the second step, how to modify the distances. So in this example, you have 2 points. One is 2 points marked. One is the location of the singular point here, which is denoted as a rectangle here or a square here. And there's another point here marked as circle. This is the miniature point. So in the previous technique, what distance we were using? We were using the distance between the singular point and the miniature point. So this, you can say that this is the original distance, or the distance which cannot be modified with respect to a fingerprint. For any miniature point, if it has a particular distance from the singular point, it will be always fixed, because if you can, since you are not able to change your fingerprint, you will not be able to change your locations also. So this is going to be fixed. So now in case of using this distance, this original distance, we are modifying this distance and we're going to use the new or new modified secure distance for the spiral curve construction. So how, let us see here how we are going to modify this distance. So to modify the distance, we are using two keys that we listed there, P naught and Q naught. P naught and and one more thing, this arrow that you see here that actually tells the direction of the orientation of this minutia point. So from the previous discussion, we are getting three things here: location of the singular point, location of the minutia point, and its orientation. Now, to get the modified distance, we have to modify the location of the minutia point, because as long as this minutia point is here, its a distance from the singular point will be same. So to get the modified distance, the very first requirement is that we should relocate this minutia point. So to relocate this minutia point only, we are using these two keys, P naught and Q naught. With the help of P naught, we try to find out in which direction we should relocate, and with the help of Q naught, we find out how much we should relocate. So P naught is the angle that this relocation line makes with the orientation line, and along that line we travel Q naught distance, and that gives the final location here. So once we get this final location, we can get a new distance. Now if we compute the distance of this point from the original, from the singular point, we'll get a new distance. So whatever distance you see here, m dis, this is nothing but the modified distance for the ith minutia point. And once we get this modified distance, we use this modified distance to make the spiral curve. So up till this point, only the difference is in the previous case, we are using original these distance measures to make the spiral curve, and here we are going to use this modified distances to make this spiral curve. Okay, and later we'll see that whatever spiral curve we get, to project it to make it a 3D curve, we make use of the ridge count. And let us just understand what we mean by ridge count, and then we'll discuss how we are going to use it. So ridge count is actually nothing but nothing but it tells you that how many ridges you count when you travel from your singular point to the minutia point that you have considered. For example, in this case, if you travel from here to here, you find that these green points are crossed, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Around 12 points are there when you travel from here to here. So this defines the ridge count. And this ridge count also you can say that this is a modified ridge count, because originally if you, let's say, travel from your singular point to the minutia location, you will only cross these red points, which are total 8 in number. But now when you compute the ridge count with the help of relocated location, you get a new value, and that is in this particular case 12. So this is also a modified ridge count. So we have actually got two modified things. One is the modified distance, and second is the modified ridge count. With the help of modified distance, we are going to make our 2D spiral curve, and with the help of modified ridge count, we are going to get the 3D version of the spiral curve. Okay. Now, procedure to make the spiral curve is similar to what we discussed in the previous case. Only the difference is that in place of using the original distances, we are going to use here modified distances. And as I just mentioned, that whatever purpose that we had behind using D naught there, that is actually served here by M naught. So there the distances were D1, D2, D3. Here the distances are M dis1, M dis2, M dis3, and so on, which are the modified distances. And there we were adding D naught. Now here we are adding M naught, which is exactly same as, the purpose is same as what we had for the D naught there. Okay. So once we get the modified distances and we add this M naught to those values, based on these values, these obtained distances, we can make this spiral curve. Okay, and obviously requirement here is also that these distances should be sorted. So M dis1 plus M naught should be less than M dis2 plus M naught, and so on. Then only we will be able to construct this curve. Okay. Now, the procedure for constructing the curve is exactly same. So I'm not again reiterating that here. Now, once you get this curve from those distances, to get the 3D version of the spiral curve, where you're making use of ridge count, And in place of directly using the risk count, modified risk count, we are using a key R0, which we are multiplying to the risk count, and then whatever value we are getting after the multiplication, that we are using to project all the points of the spiral curve to 3D. So this spiral curve, if you just project it on the XY plane, you will find that this will be a 2D curve. But with the help of that R0 into modified risk count, we are able to push it up by this much value, by these by the length of these green lines, which is nothing but the value that you get from R0 into this modified risk count. Okay, so with the help of that, this curve has been projected into 3D. So this becomes three-dimensional spiral curve. And since we have got these set of keys, we generate a new key from all the existing key that we call T0. And so T0 is not no need to be defined. It's not required to define T0. This is obtained from these existing keys P0, Q0, M0, and R0. And to get this T0, we're just converting these keys to 8-bit numbers. And after concatenating this 8-bit number, whatever 32-bit number we get, we just compute the decimal of that. And with the help of that, that value that we get here, this T0, we again further relocate the obtained spiral curve to make it more secure. So initially, if let's say there's no relocation, your spiral curve, which is in the form of 3D, it will be somewhere here, let's say. Now with the help of this T0, we are relocating it in the 3-dimensional space to make it more secure, so that, I mean, it becomes highly irreversible. The process becomes highly irreversible. Now to relocate anything in 3D, you need basically 3 things. You need at least minimum two angle to define a unique direction, and the value of the displacement. So this T0 is here. T0 defines the value of the displacement for this curve, and with the help of R0 and Q0, which are already defined keys, we are trying to find out the unique direction here. So if you apply that, we'll find that your spiral curve for fingerprints will look something like this, which is relocated in 3-dimensional space. Okay. Again, the curve that we are going to get here is also a spiral curve, or you can say it's a geometric shape. So it can be used to. So these are the geometric shapes. So house drop distance can be used here also to match them. So the matching that is done here is also based on house drop distance. Okay. Just to see the revocability, you can visualize this example. From the same fingerprint image, when key 1 was used, or key set 1 was used, this curve was obtained, this spiral curve was obtained. When key 2 was used, this spiral curve was obtained. And if you compare them, it's very easy to say that they are very, very different. So that way you can say that this technique is also highly revocable, because if you change the key, what you get is what you get is completely different from what you had previously. So here also is very much possible to revoke your compromised template and replace it by a new template if the database is attacked. Okay. To test this proposed technique, we have used these popular databases that are normally used for experimenting any fingerprint based technique. So, and there are in this FVC, there are multiple databases, but we have used FVC 2002, 3 subsets of that for testing this. And to define the P0, Q0, and P0, Q0, M0, and R0, theoretically we can define any value for P0, Q0, M0, and R0, but we have just restricted restricted the ranges for them, and we have defined these techniques in these ranges. But theoretically, you can have any range defined for them. It can be same also for all of them. Okay. So for this technique, when we compared the performance, we found that this was giving very, very good performance. And in terms of all the performance measures, it was superior to the existing techniques. We compared this with many other techniques, and we found that with all of them, this technique was superior. In some other techniques also, you see that the performance is coming ideal, but that is only coming for certain databases. It's not coming for all the databases. But this proposed technique is giving, consistent performance for all the databases that are used. So let me just conclude this by mentioning what we have discussed here. So first we discussed what is biometrics, and then we discussed what we mean by biometric template, and then we discussed what we mean by biometric template security, and then for under biometric template security, we discussed in detail. We discussed two techniques. One was fingerprint cell, and then another was fingerprint cell with imprintable features. And with this, I just conclude my talk, and I will be happy to answer.
Thank you, sir.
Yeah.
Thank you, sir, for this insightful sessions. We have, I think, few questions.
Yes, ma'am, please.
So the first question goes like, what is the scope of multimodal biometrics? When the multimodal is like face and ear,
Okay.
what is the scope of it using as a biometrics?
So basically, your question is not related to this security thing, right?
Yes, sir. In an unconstrained scenario.
Yeah. So I think though we do not have any commercial system with the ear and face, but at least the hope is that we will have good systems where we are making use of ear and face both. And the reason is that to capture the ear and face, we need the same kind of setup. And they can be, when we are capturing the face, we can also capture the ear simultaneously. So because of that, we can hope that we will get good systems where both can be combined. But I think till this point, we don't have any commercial system available where we are using both of them simultaneously.
Okay. Thank you, sir.
Yeah, but as a multimodal biometric traits, I think this combination is I think a very good combination. The reason is that I just mentioned that this does not require any extra setup. Whatever you use for face can be used for ear, and both of them are basically in some sense they can be captured even from the non-cooperative users.
Yeah, right. Thank you, sir. And one more question. How effective is to use compressive sensing techniques in MRI?
Compressive sensing technique in MRI?
Yes, sir. Sanjay sir is asking some suggestion on that.
Okay. So actually, truly I don't work on work in this domain. So maybe whatever comment I am giving may not be very insightful. But I think in the medical domain, the data, details are very important, right? So if we are doing any kind of compression on that, we should be, I think, careful about the kind of compression we are doing. We should not lose it. But since the volume of data is more in case when we are handling the medical images, there is a requirement of having the compression, but we should be careful about when we are doing the compression.
Thank you, sir. Hope it helps, Sanjay sir. So one more question we have from Professor Harshita. The question is, how optimal is template security for multimodal biometrics?
Okay, so I think in terms of optimality, we can say that if you are using the biometric template security for multimodal biometric, I guess this I can say this will make a system which is highly irreversible. That means highly secure. In terms of optimality, I don't know like what exactly she mean by optimality, but in terms of security, I can say that this is going to be very secure because when we apply the template security on one trait, it becomes reversible. But if you mix multiple traits, getting back to the original feature will be highly complicated. And like so, getting I think irreversible system is easier in case of multimodal biometrics.
Thank you, sir. So my personal question is like, so can we work with less number of data, like 100 instance of data set? Is it enough to work on it, sir? On any biometric in the initial level?
So I think that depends on the technique that we are using, because we can use any number of data set, any number of samples in the data set. But the thing is that for training, actually it all depends on what technique you are using and how much data it requires for training the system. Okay.
Like sir, if now example now one-shot learning has been in the trending era. So if they're saying with less number of samples, will it be applicable even for biometric?
Yes, sir, that is true for anything, because they are talking in general. In case of biometric, the things are little complicated or a little challenging. I can say the reason is that here the objects that we are distinguishing, they are very similar. In general, suppose if you are using one-shot learning for object recognition, in that case, the objects that we are dealing with, they may be very different. For example, we might be differentiating, let's say, a ball from the aeroplane or from the bottle or from the mobile phone. But here, when we talk about biometrics, we are comparing two faces, which are very similar. Right? Everybody has the same two eyes, one nose, same kind of placement of the mouth and so on. So the features are like very similar here. So maybe what we can achieve in case of general object recognition, we may not be able to achieve with the help of same set of samples in case of biometrics. But obviously, if you're using the one-shot learning, we can reduce the number of samples.
Okay, sir. Thank you. It was a privilege to hear from you, sir. Thanks a lot.
Okay, thank you.
So last, can you take one more question, sir, please?
Yeah, no problem. Please go ahead.
From Professor Harshita.
Yes.
Applications like security system tends to have complex data sets. Is it feasible to go biomodel as year and phase for application like surveillance?
Yes. I think these are. Maybe I think surveillance is a very good example where we can use combination of face and ear, because when we capture the data, we get both simultaneously. So I think that's a good place where the combination of face and ear can be used.
Thank you, sir. Thanks a lot for your precious time, sir. Thanks a lot, sir.
Thank you very much. Is there any other question?
No, sir. You can wind up, sir. Thank you, sir. Thanks a lot.
Okay. Thank you very much. Thank you very much for inviting me.
Dear